Hi everyone, welcome back to Chem Story. Today we're tackling a classic challenge in organic chemistry, figuring out whether a reaction will go through substitution or elimination. These two mechanisms often compete with each other, and at first glance, it can be tricky to tell which one will dominate. But once you understand the key factors, like the structure of the substrate, the strength of the base or nucleophile, and the surrounding conditions, the patterns start to make a lot more sense. So let's break it down and build a decision-making framework you can actually use. First off, why are substitution and elimination even in competition to begin with? Well, both reactions usually start from the same kind of molecule, an alkyl halide, and both require something with a lone pair, a nucleophile or a base. Here's where it gets interesting. Many species, like hydroxide or alkoxides, can act as both a nucleophile and a base. And that's exactly why these two reactions often overlap. When a lone pair-bearing species approaches an alkyl halide, it's got a couple of options. One possibility is substitution. In this case, that lone pair is used to directly attack the carbon that's bonded to the leaving group. It pushes the leaving group out and forms a new bond to that carbon. So the key idea here is, in substitution, the lone pair is used to attack the carbon atom directly. But there's another possibility. Elimination. Instead of attacking the carbon, a base might go after a beta hydrogen on the neighboring carbon. It pulls off that proton, and the electrons from the CH bond shift over to form a pi bond. At the same time, the leaving group departs, and we end up with an alkene. So in elimination reactions, bases attack beta hydrogens, not the carbon itself. And because substitution and elimination can both happen with the same substrate, and even the same reagent, they're often in direct competition. Which one actually occurs depends on several factors: the structure of the substrate, the strength and size of the nucleophile or base, the solvent, and even the temperature. So let's look at how those factors shape the outcome. Now let's zoom out and look at the big picture. How do reaction conditions influence the pathway? We can categorize them into four typical combinations based on two main features: nucleophilicity and basicity. Depending on whether the nucleophile and base are strong or weak, we get four general types, and each one tends to favor a different reaction path. Type A involves a strong nucleophile and a strong base, like hydroxide or alkoxides. Type B uses a strong nucleophile but a weak base, such as iodide or thiolate. Type C is the reverse, a weak nucleophile but a strong base, like tert-butoxide. And type D is when both nucleophilicity and basicity are weak, like with water or alcohol. If you look at the trends, primary substrates tend to favor SN2 or E2, depending on the reagent. Secondary substrates are where competition really kicks in. SN1, SN2, E1, and E2 are all on the table. Tertiary substrates are generally too hindered for SN2, so you'll mostly see SN1, E1, or E2, depending on the surrounding conditions. But the key idea to remember is this: it's all about how structure, nucleophilicity, and basicity interact to determine the mechanism. Now that we've seen the overall pattern, let's walk through some common reagents in each category. Type A reagents are both strong nucleophiles and strong bases. Examples include sodium hydroxide, sodium methoxide, and sodium amide. What sets them apart is their small size. Because they're compact, they can efficiently attack the carbon center in substitution or abstract a beta hydrogen in elimination. Type B includes strong nucleophiles that are relatively weak bases, like iodide, bromide, azide, thiolate, or acetate. They strongly favor substitution, especially SN2, because they lack the basicity to promote elimination. Type C is the opposite. These are strong bases but poor nucleophiles. Bulky reagents like potassium tert-butoxide, lithium diisopropylamide, or DBU, fall into this category. Due to their steric bulk, they have difficulty accessing the carbon center for substitution, but they readily abstract beta hydrogens, promoting elimination, typically E2, especially with hindered substrates. And finally, type D reagents are weak nucleophiles and weak bases like water, alcohols, or amines. These conditions tend to favor SN1 or E1 pathways, particularly when the substrate is secondary or tertiary, and the solvent is polar and protic. Let's start with primary alkyl halides. These are typically ideal for SN2 reactions, because the backside attack is easy. There's hardly any steric hindrance around the carbon center. Now let's look at what happens under different conditions. If you've got a strong nucleophile and a strong base, like sodium hydroxide or sodium methoxide, SN2 is the major pathway. You might get a little bit of E2, but substitution clearly dominates. And remember, this happens because type A reagents aren't just strong, they're also small, which makes it easier to attack the carbon directly. If the nucleophile is strong, but the base is weak, we're looking at pure SN2. No elimination here, just clean substitution. But if the nucleophile is weak and the base is strong, things shift. Now you get E2 only. The base acts more like a proton grabber than a carbon attacker. And finally, if both the nucleophile and base are weak, there just isn't enough driving force. So in most cases, no reaction happens at all. So the main idea here is this. Primary halides typically favor SN2, unless a bulky or strongly basic reagent shifts the balance toward elimination. Now let's move on to secondary alkyl halides, where things get a bit more complicated. At this stage, both SN2 and E2 are possible, and the reaction outcome depends heavily on the conditions. Even small changes, like switching the base or adjusting the temperature, can shift the mechanism. If both the nucleophile and base are strong, you'll usually get a mix of SN2 and E2. But in most cases, E2 tends to dominate, especially if the base is bulky or the reaction is heated. If the nucleophile is strong, but the base is weak, then SN2 becomes more favorable, since there's less push toward elimination. If the nucleophile is weak, but the base is strong, E2 takes over again. The base removes a beta hydrogen and elimination proceeds. And when both are weak, this is where SN1 and E1 come into play. Under polar product conditions, like with water or ethanol, carbocation formation becomes feasible, and the reaction follows that stepwise path. The stability of the carbocation now plays a major role as well. So here's the key. With secondary substrates, no single factor is enough. You have to consider base strength, nucleophilicity, solvent, and even temperature to predict which mechanism will take over. Finally, let's talk about tertiary alkyl halides. These are just far too bulky for any kind of backside attack, so SN2 is off the table. If you've got a strong nucleophile and a strong base, then E2 is the clear winner. Even though the nucleophile is strong, steric hindrance makes substitution impossible, so elimination is the only viable pathway. If the base is weak but the nucleophile is strong, the reaction shifts toward SN1. The leaving group departs first, forming a stable tertiary carbocation, and then the nucleophile steps in. If the nucleophile is weak but the base is strong, we go back to E2. Even without a direct attack on carbon, the strong base can remove a beta hydrogen and drive elimination. And when both are weak, we see a mixture of SN1 and E1. The reaction proceeds through a carbocation intermediate, and depending on the conditions, both substitution and elimination products may form. Let's take a look at how reactivity changes depending on the structure of the substrate. Starting with type A conditions, a strong nucleophile and strong base, like sodium methoxide in ethanol. When the substrate is primary, like ethyl bromide, substitution dominates. SN2 accounts for about 90%, and only 10% proceeds via E2. That makes sense. There's minimal steric hindrance, so backside attack is efficient. With a secondary alkyl halide, the balance shifts. Now we get 79% E2 and only 21% SN2. Both reactions are possible, but the increased steric bulk favors elimination more. And finally, with a tertiary alkyl halide, SN2 is completely out. There's simply no way to get backside attack through all that crowding. So here we see 100% E2, no substitution at all. So even though the reagent stays the same, sodium methoxide, the product distribution changes dramatically depending on the substrate. This clearly shows how steric hindrance and substrate structure can override even strong nucleophilicity. Now let's compare what happens when we change the reagent but keep the substrate the same, a secondary alkyl halide. Under type A conditions with sodium methoxide, a strong base and strong nucleophile, we saw earlier that E2 dominates, with 79% E2 and 21% SN2. But now look at what happens under type B conditions, where we use sodium acetate, a strong nucleophile but a weak base, in acetic acid. This time, we get 100% SN2, no elimination at all. Why the difference? Because acetate is a good nucleophile but a poor base. It targets the carbon directly, favoring substitution. On the other hand, sodium methoxide is not only nucleophilic but basic enough to abstract a proton, so elimination comes into play. This is a perfect side-by-side example that shows how the same substrate can behave completely differently depending on whether the reagent acts more like a nucleophile or a base. And that's it for today's lesson on substitution and elimination. I know it's a lot to take in at once, but don't worry. The more you practice, the more natural it'll feel to figure out which mechanism is most likely. So next time you see an alkyl halide in a reagent, stop and ask yourself the right questions. What's the substrate? Is the reagent acting as a base or a nucleophile? What kind of solvent is it in? Once you get into that habit, predicting the outcome becomes so much easier. Thanks for hanging out with me today, and I'll see you in the next lesson.